Compound events. A compound event is simply when we have two independent events or more that we want to find the probability of. And think about it this way. If we're going to flip a coin, and that coin could come up heads or tails, I flip it, and I get a heads. Now, just because I got heads last time, that has no impact at all on what's going to happen the next time. I could still get heads or tails. I flip it again. Oh, this time I got tails. Well, it doesn't matter now for the next time. I'm going to flip it again, and what happened in the past has no relevance whatsoever. Because each time I flip the coin, there's new probability involved. The past events don't have any impact on it whatsoever. The events are called independent. And the neat thing is that when we have independent events, the probabilities themselves don't change. Take a look at some examples here. On example 1, we have, let me pull up a pen here. We have a fair penny, and we're going to toss the penny 6 times. And each of those 6 times it came up to be tails. Now, I want to know the probability that I'll get tails on the 7th toss. Now, think about it. Just because I got tails the first 6 times, does that have any impact on what's going to happen the next time? It doesn't. I could still get heads, or I could get tails. And so the probability of getting tails is 1 out of 2, or 1/2. The reason that is the events are independent. The events are independent, and what happened before has no impact at all on what's going to happen the next time around. Now, let's see how we use the counting principle to actually find the probability now that we have an understanding of independent events. We're going to roll a pair of dice. We roll them, and we want to get 2 ones. We want snake eyes. So we're going to roll the dice. We want to get a 1 and a 1. And we want to know the probability of that. Well, we could do this a couple of different ways. We could do just like we did yesterday. We could make a tree diagram and find the probability of getting 2 ones. Take a look here. Here's a tree diagram. The first roll, 1, 2, 3, 4, 5, 6. And the second one, we could get a 1, 2, 3, 4, 5, 6 all the way through. And so, I could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, and I could write out my sample space. There are a total of 36 different possible things that could happen here, and how many of them give me 2 ones? It's just these 2 right here, the 1 and then the 1. There's a 1 out of 36 chance I get a 1 on both of the dice. Now, the tree diagram is really cool to help us find that, but it takes a while to draw it out. Imagine if you were rolling 3 dice or 4 dice. I mean, this tree would get really big really quickly. The counting principle can help us. If we take a look at example number 2, it says the probability of rolling a pair of 1s. Well, here's what we're going to do. The first roll and the second roll. So we're going to roll 2 dice. The probability of getting a 1 on the first die is 1 out of 6. The probability of getting a 1 on the second die is also 1 out of 6. We simply multiply those together, 1 out of 36. Same thing as we got from our tree diagram, but certainly much easier and much quicker to figure out. Now, example 3, we're going to use the counting principle again. Let's take a look at this one. We're going to take any of 3 buses to get to the train station. And then we're going to take either the 6th Avenue train or the 8th Avenue train to get from the station to work. and the buses and trains arrive randomly, and there's an equal chance we could pick any one of those combinations. And so we're going to begin at home, and we're going to go onto the bus to get to the station. So the first thing we're going to choose is a bus. And then we're going to choose the train. And what bus I pick in this problem has no relevance on what train I pick. What train I pick has no relevance to what bus I pick. So the probability of choosing the B bus, the probability of choosing the B bus is 1 out of 3. There's 3 buses. One of them is the B, so there's a 1 out of 3 chance I take the B. Then we want to take the 6th Avenue train. Well, there's 2 different trains. There's the 6th Avenue train, the 8th Avenue train, and so there's a 1 out of 2 chance that I take the 6th Avenue train. Counting principle says multiply, and we get 1 out of 6. There's a 1 out of 6 chance that I take the B bus and then the 6th Avenue train. On example 4, we're now playing a game that involves tossing a die and flipping a coin. And so we have a coin we're going to flip. Here's our coin. We could get heads or we could get tails. And then we're going to roll the die, and we could get a 1, 2, 3, 4, 5, or 6. And we could make a tree diagram if we wanted to, but there's not necessarily a need to. Let's just go through it and use some common sense here for a moment. What is the probability that we get tails on our coin? 1 out of 2. Okay. What's the probability that we get a 5 when we roll the die? Well, there's 6 possibilities. One of them is a 5. 1 out of 6. Now, what is the probability that we get a tails and we get a 5? Once again, we could make a tree diagram if we wanted to, but not necessary to do. These are independent events. Getting a heads or a tails does not at all impact what will happen on the die. So the probability of getting a tails is 1/2. The probability of getting a 5 is 1 out of 6, which means the probability of getting both of them, we'll use the counting principle, 1/2 times 1/6 is 1 out of 12. There's a 1 out of 12 chance that I will get a tails and get a 5. And so the counting principle guides us right through this problem. Pretty simple because they're independent events. Example 5, we have a garden nursery, and the owner knows that the color red occurs in 1 out of 15 seedlings of a certain plant. So we get these little plants. We can't tell what color they're going to be, but usually 1 out of 15 ends up being red. We want to have 200 red ones. And so the question is, how many seedlings should we plant? Well, let's see. 1 out of 15 is typically red. And we're simply setting up a proportion here. Okay, we want 200, and I almost wrote that in the wrong spot there. We want 200 of them, and the question is, how many should we plant? So to get 200, I have 1 out of 15, 200 out of how many? Well, I cross multiply and solve the proportion. X gives me 3,000. So I should plant about 3,000 of them in order to get approximately 200. So this is just another problem where we used the idea of proportions from a lot earlier in the year to determine some probabilities. So I have 2 jars, and one jar contains a red and a green marble. Second jar has a red, a blue, and a green marble. And I want to find some probabilities. I see down at the bottom here that I want to find the probability that at least one marble is red, that both marbles are the same color, at least one marble is green. And so what I'm going to do is I'm actually going to set up a tree diagram to determine some probabilities. Tree diagram is a great way to set up your sample space. In the first jar, I could pull out a red marble, and the probability of getting a red marble is 1/2. I could reach into the first jar and pull out a green marble, and the probability of a green marble is 1/2, because one of the marbles is red, one of them is green. Now I'm going to reach into the second jar, and in the second jar I have a red, a blue, and a green marble. And so 3 possible things can happen. I can reach in and pull out a red. I can reach out in and pull out a blue. I could reach in and pull out a green. The same is true down below. If I pulled a green out of the first jar, I could reach in, and when I go into the second jar, maybe I pulled out a red, maybe I pulled out a blue, maybe I pulled out a green. And the probability, it says we have 1 red, 1 blue, 1 green. The probability of getting any one of those colors out of the second jar is 1/3. And so what I'm actually going to do here is write the probabilities right next to each piece. Okay, so here we go. Now, I've written the probabilities. Let's write down all the possible outcomes. Let's create our sample space. The sample space, remember, is all possible outcomes. And what we'll do is we'll begin by simply going and saying, okay, we could get red, red. And the probability of red, red, that's 1/2 for the first red, 1/3 for the second red, and so there's a 1 out of 6 chance I get red, red. Then I could get red, blue. Probability of the red is 1/2. Probability of the blue is 1/3. Counting principle says just multiply right across. So the probability of getting a red one and then a blue one is 1 out of 6. And we'll just continue along. Getting a red one and then a green one. 1 out of 2 chance of getting the red. 1 out of 3 chance of getting the green in the second jar. Gives me 1 out of 6. And I just continue across green, red, green, blue, green, green, and I calculate the probabilities in my sample space. And by the convenience of the numbers here, they just happen to be 1 out of 6 each time. So let's fill this out. So we see all kinds of things that could happen. 1 out of 6 chance I pull a red out of the first jar, a red out of the second. 1 out of 6 chance I pull a red out of the first one, blue out of the second. 1 out of 6 chance I pull a red out of the first one, green out of the second, and so on and so forth. Now, let's answer some questions pertaining to these. The first one in part B